Hello, what's up guys, I'm Sheldon. So a lot of you are asking me about the next episode on the classifying cats and dogs in PyTorch. I'm very sorry for the delay of the episode 4 because I was busy preparing for the paper I published recently. Actually, I was busy preparing for the presentation on the conference, but fortunately everything is done now. So in this video, I would like to show you guys about the presentation on a conference where I published my paper. By the way, if you guys are interested in deepfake or deepfake detection, please leave a comment below so I can make some videos about it. So let's jump to the presentation now, shall we? Hello everyone! It has become increasingly challenging to distinguish real faces from their visually realistic fake counterparts due to deep learning-based face manipulation techniques in recent years. Today I'm going to introduce a deep learning method to detect such face manipulation. Let's take a look at the outline of this presentation first. I will first give an overview of our paper. Second, I'll briefly introduce the 3 face manipulation datasets we used in our experiments, which made it easy to compare with the state-of-the-art methods. Third, I will introduce the deep learning method to detect face manipulation. It consists of 2 stages: feature extraction and binary classification. And in the end, I will show the experimental results on public benchmark datasets, demonstrating the effectiveness of this method and make a summary. Alright, let's take a look at the overview of our paper now. Most works on detection of face manipulation resort to 2 kinds of methods: visual cues detection and deep learning detection. Here are 2 examples. In the paper exposing deepfake videos by detecting face warping artifacts, they propose a method based on the observations that current deepfake algorithm can only generate images of limited resolution, which need to be further warped to match the original faces in the source video. This figure shows the pipeline of generating deepfake images. However, such methods are often particularly designed for specific visual cues of manipulation methods, which may fail as the manipulation technology become more mature in the foreseeable future. In a paper on the detection of digital face manipulation, they proposed to utilize an attention mechanism to process and improve the feature maps for the face manipulation classification task. However, methods like this usually ignore the role of loss functions. As a result, those issues restrict the detection performance. We thus propose the following method. We take 2 videos from the dataset. In this demonstration case, the right one is the fake, manipulated video and the other one is pristine video. We then take some frames from the video and use dleep to locate the faces so as to crop it out. Next, we reshape the cropped face images to obtain a set of trained data with same sizes. Our key idea is to use a loss function for contrastive learning of 3 samples. We decide 3 samples with 2 positive samples, one is anger, and 1 negative sample, and then formulate a loss by minimizing the distance between the positive sample and the anger, and maximizing the distance between the anger and the negative sample. The backbone, which is embedded inside a triplet net, has a wide range of options. We can employ ResNet, VJJ16, exception, and etc. as the backbone. After the network is well trained, we feed all the pristine and manipulated face data into the well-trained network and obtain a set of feature points. Then we use these feature points to fine-tune a simple linear classification network. Now, with the combination of the embedded network and the classification network, we can make a binary prediction of point face images. To evaluate a network, we can evaluate the feature points visually and the predictions by performing area under curve on them. Next, I'll briefly talk about 3 face manipulation datasets we use in our experiment. We chose three major popular datasets that each has their own characteristics. The first one is called Face Forensic++, which includes deepfake videos generated with four face manipulation methods. There are deepfake, neural texture, face swap, and face-to-face. The second one is called UADFV, which is a small but commonly used face manipulation dataset. The last one is called a Celebrity DF, which is a large face forgery dataset with refined video synthesis solving common problems such as temporal flickering frames and color inconsistency in other datasets. Here, the above figures show the proportion of data distribution and the data amount in each dataset. In the following section, I will elaborate on our detection method. As I mentioned before, our key idea is to use a loss function for contrastive learning of three samples. We achieve this by resorting to the triplet loss. Specifically, inspired by the paper, Deep Metric Learning Using Triplet Network, we decided three samples with two positive samples, one is the anger, and one negative samples, and then formulate the loss by minimizing the distance between the positive sample and the anger, and maximizing the distance between the anger and the negative sample. In our experiments, we employ exception as the backbone, with modification at the fully connected layer. Note that there are three backbones in the workflow here, which share all parameters in the network. In reality, we simply feed the three samples into one network instance so as to reduce the computational requirement. We further decide a linear classification to perform binary classification to bridge the learned contrastive features with the real or fake faces. Concretely, there's 0 and 1 corresponding to real and fake faces, respectively. So now let's take a look at the results. The first one is gonna be the feature points. Here, we only show the results of different methods: neural texture, deepfake, face-to-face, face swap, and also the combination of them in Face Forensic++. The top and bottom ones are the feature points of train set and test set respectively. We can observe that the feature points in each figure are separated, forming two distinguishable clusters. Now we take those feature points and feed them into the classification network with labels. We compare the exception network, the blue ones, and our proposed model, the orange ones, on four datasets individually. Although the exception network itself is highly competent to detect the manipulative face images, our contrastive learning with triplet loss clearly enables the learning of more discriminative features and boosts the detection accuracy. We also take the outputs of the classification network and perform AUC, which is known as area under curve, on them so as to compare with our methods. In Table 3, we show the comparison of our method and the state-of-the-art methods on the above-mentioned three datasets in both intra-dataset and cross-dataset settings. For Face Forensic++, we achieved a 0.2% improvement comparing to the exception when testing the same dataset, reaching 99.9%. For the cross-dataset settings, while our method is weaker than exception when testing UADFV, it boosts 13.5% on the Celebrity DF, which is more representative than the UADFV in terms of quality, quantity, and diversity. Regarding the detector trained with UADFV, one strong competitor is FWA, which is merely 2.5% and 3.1% less than our method when testing the UADFV and Celebrity DF datasets, respectively. However, FWA achieved an AUC 18.8 higher than our method on testing the face forensic ++ dataset. It is worth mentioning that FWA is based on the observations that previous image forgery algorithms could only generate images with limited resolution, which requires to warp the fake face to match the original face. In other words, these kind of methods detect the forgery face based on the imperfections of the manipulation algorithm, which can easily be obsolete. This disadvantage becomes significant on the celebrity DF. In this regard, our method has better generalization ability. We also observed that when training on UADF-V, Method 7 ranks the second and the third place when testing the UADF-V and Celebrity DF, respectively. We also show outstanding performance of our method on the Celebrity DF, which is a relatively new, larger dataset in higher resolution with refined videos. Note that it provides noticeable different information for the network to learn. When testing the other two datasets, the loss of such information may cause the variation on the performance. Now it's time to summarize the paper. We have introduced a deep learning approach for detection of face manipulation. It first learns the contrastive features, which are then taken as input to a simple binary classification network. Results show that our method is effective and outperforms state-of-the-art techniques in most cases. Since there are still noticeable space for improving the cross-dataset detection performance, we would like to design more effective face manipulation detection techniques with high generalization capability in the future. So this is the end of the presentation. Thank you for your treasurable time. Please do not hesitate if you have any questions. So if you've come to this part, that means you're kind of a genius, like me. Okay, who am I kidding? But in that case, please subscribe and thumbs up. I'll see you next time. Bye.